let's see. Marissa,
Yes, I'm here.
gotcha. You've done pretty well in attendance. That's good, except for a little small spot. Monica Hickson,
Here.
you've done real well too. That's good. Rebecca, I've got you. And are you going to be okay now, Rebecca?
Yeah, I hope so.
Yeah.
Thank you.
I
Thank you.
got you. Vanessa, are you there? No, Vanessa. Oh, wait. Vanessa popped up with sign language. Gotcha. All right, you guys. For some reason, on Monday, I covered matrix solutions 6.3. So you got to make sure you watch that film because that's really, really tough stuff. Ryan, I got you marked in. Indira, you have a question? Okay,
Yeah,
so what's
you
your
mark
question?
me.
Pardon me?
You don't call me.
Yeah, I did. Well, if I didn't, I have you now.
Oh, thank you.
Very good. All right. So for some reason, we got out of sync, and I covered the exponential or matrix solutions in linear systems on Monday. Today is Wednesday, November 2nd, and we have to cover 4.5 exponential growth. And we have to cover it because it's on the test. So I'm going to go back to that. And if anybody can be willing to help me annotate someone that comes in late, I'd be appreciative of it. So I'm going to take you to the book. It's already prepped that class. And I think I got to go backwards here. I'm sure we didn't do this. Nobody here recalls us doing this class. Exponential growth and decay modeling. Anybody? We didn't do this, did we?
No, we didn't do that one.
Just want to make sure. Now, this is a really, really interesting chapter. It may not be to you initially, but it is good stuff. And the reason why it's good is because with our calculators, we can solve complex problems. Now, this will be Greek to many of you all in the sense that you won't really understand it, or it won't make sense. But I think that once we get through this, you'll understand it because there's really only a couple mistakes you can make as long as you have the formula. So in an exponential growth or decay model, excuse me, things are growing or dying. And they're talking here about population in the world. And pretty much it's been growing exponentially. At least the models show it that thus far. So look, in front of you, you see the exponent, the k, in your model increasing. So that means the k would be positive. If you look at left, exponential decay, the k would be negative. Now, there are other parts of the model I want to talk about. A to the O is the initial number being considered in the problem. For example, if we're talking about population of the world in 1960, and then you're going to compare it to 2022, the initial one's 1960, that goes there automatically. We'll see some examples. Okay, so here we go. And there are a couple of models to use. This is an exponential model. Why? Because there's an exponent. Maybe my tie is a little tight. Anyway, let's read the problem. We have to understand this one before we can really go on. So it says in 1970 to 2010, they decided to look at the population of the United States. So they're using a model. It said in 1970, the population was 203.3 million. Look under A, where that 203.3 is, it's A to the O because that's the initial amount. Now the A in front of it is the future amount. So you don't see it yet, but AO always stands for the first amount. The A on the other side stands for the future amount because we're trying to calculate here whether the population K is growing or K is decreasing. We know it's going to be increasing. It's positive. You can see by the graph on your left. So if we slide down a little further or to the next page, notice that we have the 308.7 on the left. And they want us to calculate it for a time of 40 years. Now, where did they get the 40? If you look at the problem, it says from 1970 to 2010. That stands for 40 years. And they want to determine what the growth rate was. That's your K. So every piece of the puzzle in front of you, the A, the AO, and the T are there. We're trying to calculate the K. Again, AO is the initial population, 203.3. A is the future population, 308.7. E is the Euler. That's a fixed number in your calculator. We don't know K. It's in the exponent. That's the percent of growth. And T is time, and we got that by taking 1910 or 1970 and subtracting that from 2010, which gave us 40. Is there any questions about any piece of this puzzle that you see the second line above? 308.7, 203.3, K, and 40. Anybody see anything in there they have a question about? Can you all still hear me?
Yes.
Yes.
Okay. Yes.
Okay. So now, we're going to go to the third line. How did they go from the second line to the third line? They have, the book does this to mess you up, I think. But what they did is they divided the right-hand side by 203, so you get E to the K 40. If you divide the right by it, you got to divide by the left, and they switched it. Does that make sense to anybody, what you see?
Yes, yes, there.
So if you look at the third line, actually the second line, well, technically it's the third line, where it starts with the E to the 40K, they simply switched the left-hand side to the right-hand side. They divided the left-hand side by 203.3. That means it goes away because anything over itself is 1. But if you divide the right by 203.3, you have to divide the left by that, and they put it on the other side of the equal sign. Now, why they did that, I don't know. I guess to get the variable on the left-hand side so people read left to right. Now, anytime you have an exponent in the that is a variable is in the exponent area, you have to use ln. Now what happens then? The 40 goes in front of the ln, the 40k, but you have ln over e. Now 40k goes in front of the ln because of the power rule. But ln over e is like saying 10 over 10 and you get 1. So it goes, those cancel out. So you're left with 40k. But if you take ln on the left, you got to take it on the right. Now to get k by itself, divide the left by 40, they divide the right by 40. Now, the issue is this. You need to be able to put this stuff in your calculator to get the right answer. Now I'm going to put it in my calculator. I'm going to show it to you. And the key is to use parentheses. We'll get the answer 0.01. Now 0.01 says approximately is the K. That stands for the growth. That means that the population of the world is increasing. Duh. But this is what it is by 0.01. So now I'm going to go to my calculator. You should be able to see it. And it's lit up. So in order to solve this problem, we're going to take the ln first. It's in parentheses. We said we're going to take 308.7 and divide it by, still in the same parentheses, 203.3 close our parentheses and divide all that by 40. Hit enter. And you get 0.010, which is exactly what the book says, approximately 1. Now, putting this in your calculator for some can be tricky because you must use parentheses. But anybody try it out there and get it? Can I get an amen from somebody out there that did this?
Yes, I did.
Rebecca, you got it? Wow, good for you.
Yes.
Okay, so now that we see that this is growing, we can now do a lot of beautiful things with that same formula. What will that be? Let's take a look. So now that we know that the growth model is 0.01, notice we can substitute the K with 0.01. Look at A, that's the future growth of 203.3 E times time. Now, what they want to know is this. Based on your model, now remember, this was 308 that we used up above. But now we want to know when will the population reach 335 million? So beginning number was 203.3, but the future one is 335. We don't need to calculate the K anymore because we did that. We want to know what T is. Before we had T, now we don't have T. I'd like a good glass of tea right now. No, excuse me, wrong subject. I say, what's wrong with that guy? So look, they switched it automatically. They took the 203.3, divided on the right. If you divide it on the right, you get E 0.01T, and then you have it on the, and they switched them again. The third line is divided by 203.3. That's why you only have the E to the 0.01T on the left. Now, let's go over to the radius. So I want to be sure, does everybody see how we got to the third line? Because a lot of folks don't see that.
Yes.
Everybody good with that?
Yeah. Yep.
Okay. Okay, so let's go on then. Since we have t in the exponent, the only way we can bring it down to solve it for this method in this class is we use ln. When you use ln, the 0.01t goes in front of the ln, but ln and e cancel on the left. On the right, it stays the same. So now we're going to do the same thing. They want to know what time period will we get using this information. And they get 50. Well, 50 is from 1970, so that stands for 220. But let's see if we can calculate it. See, part of this class is not just being able to do that, but understand what it means. The 50 stands for 50 years from 1970. And of course, the population of the world is supposed to be, according to this model, 335 million. Now, somebody could Google that and see what the population of the world is, see if they're off or not. But let's do this first. Let's pull in our ln, 335, and that's divided by 203.3, same as the other one. Then all that's going to be divided by 0.01. And let's see what we get. Let's go back to our calculator. We're going to take our ln first, 235 divided by 203.3, close our parenthesis, and divide all that by 0.01. And we know we're supposed to get 50, and whoa, what happened there?
Oh, you put 235, not 335.
Yes, I thought I clicked on the right thing, but darn thing. I hate that when calculators do that. And then they're going to blame your fingers. See if I can mess it up twice. And let's hit this. 49.9, it's like 50. Perfect. So now the question is, are there 335 million people in the world? Let's take a look. Let me Google this. Somebody else may have already done it. Oh, that wasn't for the world. That was for some other country. My bad. That was the population of the United States. So go back to that. Current US population. Well, can you guys see what I brought up?
No.
You can't see that? Anybody?
No, again.
So nobody sees this map of the United States?
I see it.
I see that.
Okay, so you can see the population is a little bit more than what our calculations is a little bit less than our calculation, but it gets it pretty close. About 332 million. Oh, and this is 2021. So that was 2020. So, we lost a lot of people. Oh, well, here's what they predicted. Right. Look at that. 335, 522. But we lost some people because of the COVID and stuff. And people stay inside. So I don't know. But it's pretty cool. It worked pretty good. So I hope everybody understood this one. I'm going to go to the next one. Everybody still breathing all right?
Yes.
Yeah, good. Now, this is the Dead Sea Scrolls one. I'm not going to do this one right now. We'll come back to it if we want to, but it's the same problem exactly. What I want to do is this next one. Because this is relative. Flu. This is a formula relating to a small town with 30,000 inhabitants that has an outbreak of flu. The formula says you have 30,000, that's the most people in the town, over 1 plus 20e to the negative 1.5t. Now, the negative is in the denominator, and don't let that fool you, because I said negative means decaying. In this case, if you put a negative in the denominator and you move the numerator, it means more people were getting flu than less. So the first question is, A, how many people became ill with the flu when the epidemic began? Well, this is not a very good thing. The question should really stay, how many people were ill when the flu first hit? Because on any given day, you're going to have people sick. So before day one, before this hit, what day is it? What day would it be? It's day 0, right? Everybody okay with day 0?
We don't see a. Are you supposed to share your screen? We don't see a book or anything.
You don't see the book?
No.
Let me go back. I don't know why. Can you see it now? It says you can.
Yes.
Thank you for letting me know. So look, if you're talking about a disease hitting your town, day 1 is the beginning of the disease. But before day 1 is day 0. That's before it hits. First day of disease is day 1. Second day is day 2. Before it is day 0. So notice if you put, can you all see the formula there? 30,000 plus 1 plus 20e negative 1.5. Can you all see that?
Yes.
So where would we put the 0? No, you guys are not talking so much. Let me have to pull out my whiteboard now.
Where the T is? Where the T is at?
Yeah, exactly. So let's look at this more closely. The formula says you have 30,000 divided by 1 plus 20 Euler to the negative 1.5, and we said t is going to be equal to 0, right? Everybody agree with that?
Yes.
Okay, what's 0 times anything?
0.
Okay, so the next line would be 30,000 over 1 plus 20 e to the 0 power. What is e to the 0 power?
1.
It is 1. So now you have anything to the 0 power is 1. Doesn't matter. It's an elephant, it's 1. So now I have 30,000 over 1 plus 20 times 1. So that's 30,000 over what? What is that? Somebody know?
Divide by 20.
What
One.
what's it going to be? What's it going to be divided by?
21.
Yes.
21.
So if you divide this by 21, this will tell you how many people were sick in the city before the disease hit. And you should get 14 to probably 9 because it's 5-7, we'll round up. It was really 14 to 8.57. But that's more. So we'll say this many were sick. Everybody okay with that?
You may round it up.
Pardon me?
Should we round it up? Should we round it up? Round it?
Yeah, because you can't have a half person sick.
Mhm. Okay. Thank you.
So we got 1429. Now let's take a look and see if that's right in the book. See what the book says. If it doesn't have it right, it's possible. Yeah, 1429. That's how many people were sick before it started. Yeah, anything to the 0 power is 0. 20e to 0 is 1. 1 times 20 is 20. So you have 30,000 divided by 21. Now look at the next question. Let's do C. We'll go to B in a minute. What is the limiting size of the population becomes ill? What does that question mean? Can somebody tell me? Somebody that hasn't spoke. Someone, let's try to get out of here tonight.
Is it 0?
It says, what is the limiting size of the population becomes ill? That's the limiting size. What does that mean? Anybody have an idea what it means?
Population of ill people.
And
The
the
amount of
measure
people that
maybe?
can become ill.
The least number of population that is ill.
No? What is the limiting population?
Does it mean all the population?
Yeah, that's the most that can get sick. So what is the most people that can get sick?
30,000?
Yes, that's the limiting population. The most people that can get in this sick in this town is everybody. So it's limited to 30,000. You can't get any more sick than that. Are there any questions about that?
Total number, right?
Pardon?
The total number.
The total possible number of getting sick is 30,000.
Yeah, the total number.
So now we're going to go to B. How many people were ill at the end of the 4th week? Well, what do you think you're going to do?
We put 4 in T.
Yeah, exactly. So in practicing, you want to put everything in the bottom in a parenthesis. And I'd like to see you do it. And let's look at the next page. So they put 4 in there, and we get 28,583 people get sick by the end of the 4th week. That's almost the whole town. Would you guys like me to demonstrate that?
Yes.
Okay. So we're going to do the same thing as we've had before, except for the T, we're just simply going to put in 4. That's all we're going to do. So let's go to our calculator. You should be seeing the calculator. No, you won't see it. Nah. My calculator went to sleep on me. See if we can find it now. Well, doesn't want to pop up for me. There it is. All right, so we're going to start all over. Can you all see the calculator now?
Yes.
Okay. I have a all right, my notes, I'm going to put 30,000 in, just like we have before. 1, 2, 3. We're going to divide this by, and we said we're going to open up with parentheses. We're going to put 1420E. Remember, here is the Euler. Have to hit second, E. And then we're going to put a parenthesis up there as well. Negative, not minus, 1.5 times 4, and then push it out. Now, if we hit enter, now we have all the parentheses we have. Notice, if I hadn't had that other parenthesis, it wouldn't have been complete. Some calculators will work without it, but let's see. This one will. Well, heck. I'm thinking you guys can see it now. Let's try it again. And the answer is not correct. Let's see what happened. Let's look at our book. The issue is not that it's the calculator's the issue. And I don't know if because it messed up or what. 1 plus 20E. I probably messed it up. It's supposed to be plus. I think I messed it up. I didn't look at the thing correctly. Yeah, let's try it again. I don't even want you to see it. All right, 30,000. There it is, divided by, open parenthesis. It was 1 plus, correction, plus 20. Now the Euler. Now up the top, it's a negative 1.5 times 4. Close our parentheses, push it out, and close our parentheses again. Now let's see what we get. Yeah, 28,583 people. So everybody okay with that? Does that make sense? Do you see how to do it with your computers, your calculators?
Yes.
Yes.
All right. Is Gabriel here? Gabriel Mulvaney?
Yes, right here.
All right. Thank you. All right, let's go. Glad that you're with us, Gabriel. Let's go back to our book. This was a very interesting problem. I spent a lot of time on it, but I wanted you to be able to figure out how to do this. Now, let's look at the left, modeling data. Exponential starts to go up and up and up. That's growing. And then exponential decaying is the second one. Log kind of goes up and gradually comes down. Same thing for decaying. Linear growth is up, linear growth going down. Now, if you look at example 4 and you compare it to the others where it goes up and then gradually levels up, this is a logarithmic function. So if you're showing something like this, you should be able to figure this out. Now, look, this is not hard. You should never worry about something like this because this is in fact pretty easy. So if you have a line that's going like this, that's a kind of a log problem. This is increasing. The other one was like this, then decreasing or decaying. You have a line that's going like this, that's linear and that's increasing or growing. You have one going like this, it's decreasing and it's decaying or dying. Now, exponential goes like this. It gets bigger and bigger and bigger, and it doesn't quite go on a straight line. Maybe it looks better like this. Notice how the spots get bigger and bigger and bigger and bigger, and they do kind of angle out, and that's increasing. So that's what they're trying to show you. So you only have two choices: the straight line, the exponential, which goes like this, or the log one that kind of goes like this. So if you had to pick one, you should be in good shape. So now let's go back to the book. So now you can see example 4 is clearly logarithmic. Now there's a way to do all the calculations. We don't have you create linear regression models anymore. That's good to read. So now look at the left. What kind of model would you pick for this? Well, 2.6 to 3.0 is 4. Then it grows by 7. Then it goes by 8. So it's not linear. It looks like it's exponential. Remember how I showed you? And now you're measuring vertically, and it's getting farther and farther apart. So if you had to pick a model for figure 4.25, you would say it is a exponential model, or it could be a log one, but this is exponential because it keeps increasing. It doesn't level off. Does that make sense to most of you out there? Everybody good?
Yes.
Okay, now we're going to compare two models. We're going to look at, I guess, a linear model and an exponential model. Let's take a look. So they give you two functions. The f of x1 is linear. The g of x is exponential. Why? Because you got an exponent. You all can see the x is in the exponent area, right, in the g of x model? Or I can call it an equation if you want. So they want us to put in 51 and see what the world population will be, or whatever population trying to figure out, will be at 51 after 49. So that's the year 2000. It shows the world population is 6.1 billion. Now, the reason why they create this model, you're going to say, well, we already know what it is. It's because to prove the model works. Now, here's the caveat. We're going to compare both these models. And they'll look the same initially, but they are not. So look, if you put 51 in your calculator, multiply it out, you get 6.1 billion. If you put it in exponentially, you're going to get 6.1 billion as well. Let me demonstrate. I guess I could demonstrate them both. Then the second would be, and they're comparing both models. And you're going to see, well, which one works the best. So let's go to our whiteboard. Or let's go to the calculator. So in the calculator, we'll put the linear model in first. We'll 0.074 times, they put parentheses, we don't need to, 51. And then plus 2.294. Hit enter. You get 6.06 billion. Let's put in the other one now. 2.577 times, we have to use parentheses here, 1.017. Close our parentheses, upper arrow is 51, that's our exponent, and push it out and hit enter here. And you get the exact same number, except for it's carries out further. So you might say they're both the same. Well, I'm sure you've heard of this before. There are things called model breakdown. That means over time they don't work anymore. So let's take a look. Back to the book. Now, let's look at the year population 77. That's year 2026. If you put 77 in the exponential model, or the linear model first, you get 8.0 billion. If you put 77 in for the exponential model, you get 9.4 billion. That's a huge difference. One of them's right and one of them's not right. You're going to say, well, how do you know? It says by other projections, the world population is expected to reach 9.3 billion by 2050. Well, what is the deal? That has nothing to do with it. We want to know about 2026. Look at the last line. The linear function f of x serves as a better model because the world population is really projected to be 8 billion and not 9.4. So the exponential model is no bueno. It gave us the right answer for the initial one of 2024 or whatever it was. But for the year that's later, 2026, or it was 9.4 billion. No bueno. Now, this is the last problem. You can write this problem in g of x form here. This is an exponential form. Or we can write it in base e. You will get the exact same answer. And I want to prove that to you. So the g of x model shows it in exponential form. So you have 2.577 parentheses 1.017 to the x power. And we'll get a number. Let's just do that one first. Can you guys see my calculator?
Yes.
Thank you, Marissa. Appreciate that. 2.577 I'm going to put in here. Open parentheses because I'm going to times it by 1.0. Well, actually, I need to times it by. I did the wrong model first. Let me back up here. We're going to do the linear ones. We're going to do 0.0. Oh, wait. My bad. I'm way off. The exponential one. I'm sorry. Different number though. 2.5. So I have numbers all in place over here. 77. 2 sevens. Back one. Delete. Open parenthesis. 1.017. Close parentheses. And we're going to make it to the x power. Now we can plug this in our calculator. It's going to give us an answer. Boom. 3.050. Now, I'm here to prove to you that the ln version is going to give you the exact same number. So you're going to say, that's hard to believe, but it is. So we're going to go back to the book, give you the second comparison. 528, it's on the book. So now we're going to use the g of x formula, which says you have 2.577 e 1.017, and that's in your exponent. Let me see if let me write this down correctly here. 2.577. And then we put down our E, and that's going to give us ln at the top. 1.017, close parentheses, and then x. All right, let's see if we can put this one in our calculator. This is no different than anything else we've done. I just have to be sure I do it right. Here we go. We're going to show it right here. 2.577 first. The Euler, do second. And here's our Euler. Boom. We said we're up to open parentheses here, and then we're going to stick ln up there. Little tiny ln. Then 1.017. We're going to close our parenthesis there. Put in our x. And push it out to get the answer. I think it's written correctly. Let's see if it is. And it's the exact same thing. You would think, well, what the heck? All that other stuff, and you get the same answer, and then it works. And you guys know it works. Why? Because E and ln are something like 10 over 10. They cancel. You're left with 2.577 to the exponent of 1.017x. All we did was take E and divide it by ln, and we get the same thing. Well, look, we covered what we should have done on Monday, and on Monday we covered what we should be doing today. So we've got everything in sync. Let me go over my attendance to make sure I've got everybody accounted for. And when I do so, I'll call your name. If you want to hasta la vista, you can. Let me just see. Did Nikki didn't make it in today? Okay. Just who else didn't make it? Alma Garcia, are you here? No, Alma? Can't hear. I guess she's here. No Gillis's. No Jordan. I got you, Alma. Lillian Holmes Hancock, we're missing you. If anybody knows her, tell them we're missing her. Reba Culsum? No Reba? Rosio Morales. Rosio, where are you? see who else. Edith, you're here, aren't you? No,
Yes,
Edith?
sir. Good night, sir.
All right.
Yes, I'm
got
here.
I got you. Venencia, you're not here. How about Joshua Trail? Listen, Joshua. Holly? No, Holly. And Erica tried to get in, but I don't think she's here. So I don't have any questions for you all. Do you have any for me?
No.
No.
All right. See you guys.
Good night.
Good
Have a
night.
good night. Thank you.
So much. Thank you very much.
Good night. Good
Night.
night. Bye, Sharon, Indira.
Good night. Thank you.
Good night.
Bye.
Good night.
Good night.
Good night.
Bye, Dylan. Monica. See ya.
Bye.
Bye. Reba, Colson, you're here. It doesn't show you here. I'm going to mark you in. I got you, though, Reba. Can you hear me, Reba? I got you, Reba.